8.5, the Cartesian equation of a plane. So let's recall, to find a vector n equals ABC, and again, this is the normal, right? That is perpendicular to two vectors, vector A and vector B. What we do is we have to find the cross product of vector A and vector B, okay? And then the notation for that is vector A cross vector B. This is not multiplication, it's a cross product. So the normal axis for the plane is the only possible line that can be drawn through the origin, 0, 0, 0, perpendicular to the plane. In any diagram below, ON, so if we have O, it's origin, and then N is going to be that normal vector ABC, okay? And then obviously repositioned at the origin, right, ON, is the normal on the plane because it joins to N, the origin to N, a point on the normal axis. Any non-zero vector is a normal to the plane if it lies along the normal axis. Okay, and here's a blurb. The Cartesian equation of plane, and that's what we're going to be focusing on in our cube, so like 3D, is ax plus by. Now, we're extending this, right? Plus cz. We now have 3 dimensions, not just 2 dimensions. Okay, plus d equals 0, where vector n equals ABC, right? That's the normal vector. And vector n is a normal to the plane. And vector n equals vector A cross product vector B. Okay, and then just note vector A and vector B have to be 2 non-collinear direction vectors. So they can't be the same direction vector, they have to be unique. So 2 planes whose normals are n1 and n2 are parallel if n1 is a scalar multiple of n2 for any non-zero number k. Okay, obviously if it's 0, we're just going to have 0 equals 0, so that's not going to work. So we have to have some non-zero vector here. Okay, our perpendicular only if the dot product of the normals is 0. Okay, and then obviously have an angle between the planes determined by, the long form of the dot product. So cos inverse of the normal 1 dot normal 2 over the magnitude of normal 1, magnitude of normal 2. Okay, so we've seen these before. So that's just a recap. Okay, so example 1, here we go. The point A, 1, 2, 2 is a point on the plane with this normal. Okay, determine the Cartesian equation of the plane. So, as a reference, so the Cartesian equation is always going to start off as ax plus by plus cz plus d equals 0. Now, the normal represents the ABC, so we can go ahead and sub that right in. So we can sub in negative 1x plus 2y plus 6z plus d equals 0. Okay, so when we actually find the Cartesian equation of the plane, what's going to happen is it's going to look like this, except for we're going to actually find the d value. Okay, the d value is our goal here. So we're given the point 1, 2, 2. So as long as we're given the normal and any point on the plane, we're able to find that d value. So let's go ahead and sub in 1. And then plus 2y is 2, plus 6z is 2, plus d equals 0. Okay, and all we have to do is solve for d. So I get negative 1 times 1 is negative 1, plus 2 times 2 is 4, plus 6 times 2 is 12, plus d equals 0. Okay, so then we get negative 1 plus 4. That's going to give us 3, plus 12 is 15. So if we have 15 plus d equals 0, we bring the 15 over, we get d equals negative 15. Okay, so we just found our d value. So we can say that the Cartesian equation is going to be, again, we're going to reference back here, but this time we're going to sub in our d value. So it's negative 1x, so I'm just going to put negative x plus 2y plus 6z minus 15 equals 0. So here's the thing. Usually what we want to do is this leading coefficient, we always want it to be 1. So what we can do is we can multiply or divide this equation by -1 to give us x minus 2y minus 6z plus 15 equals 0. These two are equivalent, and that's going to be our Cartesian equation, okay? So we can just say like make positive, or positive sign. Okay, example 2, determine the Cartesian equation of the plane containing these 3 points, A, B, and C. Okay, so we have 3 points. We know that we need to have 2 direction vectors because what we need to do to those direction vectors is cross them to find the ABC. Okay, like the normal. Okay, so let's do that first. Okay, we're going to find AB as a direction vector. Okay, so let's go 3 minus -1. Okay, 2 minus 2. And 4 minus 5. Okay, as a recap, we're doing B minus A. So our first direction vector is going to be 4, 2, -1. Now, let's do direction vector BC. Okay, so we're going to go C minus B. So we have -2 minus 3, -3 minus 2, and 6 minus 4. Okay, so vector BC is going to be -5, -5, 2. Okay, now that we have 2 direction vectors, what we want to do is we want to find the cross product. Okay, so I'm going to go down here. We're going to do vector AB cross vector BC. So we're going to list them both twice, 4, 0, -1, 4, 0, -1. And then -5, -5, 2, -5, -5, 2. So what we're going to do is, and I'm going to do this kind of in my head, 0 times 2 is 0, minus -5 times -1 is 5. Okay, -1 times -5 is 5, minus 2 times 4 is 8. And then we have 4 times -5 is -20, minus anything times 0 is 0. Okay, so for the cross product, we get our normal vector to be -5, -3, -20. Okay, I'm going to multiply this by -1 so that we just get the positive, 5, 3, 20. Okay, and this makes sense because when we put it into the Cartesian equation, we want that leading coefficient in front of the x value, which is 5 from the normal, right, the A value, ABC. We want that to be positive anyway. Okay, now that we have the normal vector, I'm going to go back up here. Okay, our normal vector was 5, 3, 20. So we're going to have 5x plus 3y plus 20z plus d equals 0. And again, we're back to the exact same goal. We need to find d. So we can plug in A, B, or C, it doesn't matter, and we're going to get a d value. So looking at these, I kind of like the positive values, right? I like the small values, and then I like the positive values. Okay, I'm going to pick B. You can pick A or C, it doesn't matter. You're going to get the same answer. Okay, so I'm going to go ahead and sub in 3, 2, 4. So 5 times 3 plus 3 times 2 plus 20 times 4 plus d equals 0. Okay, all I did was sub this in, sub this in, and sub this in. So I get 15 plus 6 plus 80 plus d equals 0. Okay, I get 101 plus d equals 0. Move that to the other side. I get d equals -101. So again, the question is determine the Cartesian equation. We can't just determine all of the different values in it, we want to actually rewrite the Cartesian equation. So we're going to get 5x plus 3y plus 20z, now minus 101 equals 0. And that's going to be our Cartesian equation. Example 3, determine the Cartesian form of the plane whose equation in vector form is this. So we have a point, we have direction vector number 1, and we have direction vector number 2. So what do we need to do? Well, we need a normal. So our normal is going to be when we cross product direction vector 1 and direction vector 2. So let's go ahead and rewrite direction vector 1 and 2 twice. So 1, 0, 2, 1, 0, 2. And then negative 1, 3, 4, negative 1, 3, 4. So we get 0 minus 6. So I'm just going to write negative 6. Then we get negative 2 minus 4. Then we get 3 minus 0. Okay, so our normal is negative 6, 3. I'm going to divide this by negative 3. Okay, so I'm going to get 2, 2, 1. Remember, you can always have a scalar multiple for a direction vector or a normal vector, and they're going to be equivalent. Okay, because they're not a measurement, they're just saying what direction is it going in. Well, going into 2, 2, 1 is the same if you extend it into the other way as negative 6, 3. So now we have our normal, which is our ABC. So let's put that into the Cartesian equation. So 2x plus 2y plus 1z plus d equals 0. Okay, and then we can take this point and we can plug it into the x, y, and z. So 2, 1 plus 2, 2 plus negative 1 plus d equals 0, and we solve for d. So we get 2 plus 4 minus 1 plus d equals 0. 2 plus 4 is 6 minus 1 is 5 plus d equals 0. And bring over the d, we get d equals negative 5. So again, the original question is determine the Cartesian form of this equation. So we have to rewrite 2x plus 2y plus z minus 5 equals 0. These two are the same. Okay, this is just the Cartesian form, and then this is just the vector form. Part B, determine the vector and parametric equations of the plane with this Cartesian equation. Okay, so what we want to do is, initially I'm thinking, okay, so I know our normal vector. I know a vector that's perpendicular to this plane. Okay, 1, negative 2, 5. Okay, so what we're going to do is we're going to take this equation and see x, we're going to isolate for x. So we're going to go ahead and bring over these three values. So I get x equals 2y minus 5z plus 6. And what we're going to do is kind of like a trial and error. So we're going to choose y's and z's. So all all of them are integers. Okay, because usually when we do, like, say for example, direction vectors, and we have a value that's a fraction, we usually get rid of the fraction by multiplying it by some constant. So we want to just like focus right off the bat on all being integers. Okay, so let's try just like y equals 0 and z equals 0. Okay, what are we going to get? So I'll do the work on this side. So if we have x equals 2, 0 minus 5, 0 plus 6, well, x is going to equal 6. Okay, so we're going to have a, which is going to be 6, 0, 0, and that's just a point. Okay, let's try another combination. Let's just try 1 and 1. Y equals 1, z equals 1. So x equals 2 times 1 minus 5 times 1 plus 6. Okay, so 2 minus 5 plus 6. So our x is going to equal 2 minus 5 is negative 3 plus 6. We're going to get 3. So we can have some point B that's going to be 3, 1, 1. Okay, and again, you can choose any values, and all we're doing is we're trying to find 3 points that lie on this plane. Okay, so the next one, let's choose y equals, let's go negative 1. Okay, and then z equals 1. Why are you going to introduce another negative if you don't have to, right? So let's find the third point. X equals 2 times negative 1 minus 5 times 1 plus 6. So I get negative 2 minus 5 plus 6. This is negative 7 plus 6. I get negative 1. So our third point is negative 1, negative 1, 1. Okay, just be careful. Do not multiply this by negative 1. It is a point. Points are very specific. It is not just a general direction. Okay, so direction vectors and normals, we can multiply by a constant, and we can multiply by like a negative, but points are precise. Okay, so now what we have is 3 points. Okay, I'm going to list them. We get 6, 0, 0. We have point B, 3, 1, 1. And we have point C, negative 1, 1, 1. Okay, let's find 2 direction vectors. So let's try to find AB. Okay, so we're going to go B minus A. So 3 minus 6 is negative 3. 1 minus 0 is 1. 1 minus 0 is 1. I'm going to actually multiply that by negative 1. Actually, multiplying by negative 1 actually gives us BA. That's fine. We can leave it. Okay, let's try to find BC. So negative 1 minus 3, we get negative 4. Negative 1 minus 1, we get negative 2. And 1 minus 1, we get 0. Okay, we can leave these. And what we're going to do is we are going to find the cross product. So AB cross BC. Okay, we have 2 direction vectors from 3 random points that we found. And now we're going to do the cross product. Oh no, we don't need to find the normal. Okay, now we have 2 direction vectors and we have 3 points. So we can go ahead and write the vector form of an equation of the plane. So let's put the point first. So we can just choose any point. Let's choose 6, 0, 0. Okay, plus, and then we're going to do parameter S, negative 3, 1, 1, plus parameter T. Okay, and then the next direction vector, negative 4, negative 2, 0. Okay, so with general direction vectors, we could have multiplied that by negative 1, and we could have multiplied or divided this by negative 2 and got it a little bit smaller. At the end of the day, it doesn't matter. Okay, but if we did, we would have just have, because it is nice for simplest form, we would have just had 3, negative 1, right? So we would negate this direction vector. All of these values would flip signs. And then plus t, and we would have 2, 1, 0. Okay, so now let's write parametrics x, y, z. So let's take the first 3. Okay, we're going to go 6 plus 3s plus 2t. By the way, s and t are elements of the real number system. Now we're going to take the second 0, negative 1, 1. So 0 minus 1s plus 1t. You don't have to write it like this. You can just write negative s plus t. Okay, and z, we're going to do the last one. So 0 minus s, and then plus 0t. So, in other words, negative s. Determine if planes are parallel or perpendicular. Okay, so let's talk about perpendicular first. Perpendicular planes. So again, we denote a plane using a pi symbol. So pi 1. So plane 1 and plane 2 are perpendicular with normals n1 and n2 respectively. Respectively just means for like in order, right? For plane 1 it's n1 and for plane 2 it's n2. Okay, their normals are perpendicular. Okay, so n1 dot n2 equals 0. Okay, so I'm going to give you an example. So if we have the blue plane, then this normal is perpendicular just to the blue plane. Now, if we have the red plane, this normal is perpendicular to the red plane. And also, their normals are perpendicular. Okay? Now, let's talk about parallel planes. What goes on in these ones? So, if plane 1 and plane 2 are two parallel planes, and they have normals n1 and n2, okay? Their normals are parallel. That is, their normals are scalar multiples of one another for all non-zero real numbers k. Okay, so if you have parallel planes, then their normals, which are perpendicular to the plane, are obviously going in the same direction. They have to be going 90 degrees to the planes that are going again in the same direction. So, example 4. Show that planes, okay, so this is A, 2x minus 3y plus 1z minus 1 equals 0, and plane 2, 4x minus 3y minus 17z equals 0 are perpendicular. Okay, so if we want to show that these two are perpendicular, let's first identify normal 1, 2, negative 3, 1. Okay, and let's identify normal 2, 4, negative 3, negative 17. And what we want to do is we want to show that these two are also perpendicular. Okay, so what we're going to do is we're going to do normal 1 dot product normal 2. And we're going to show that this equals 0. So 2, negative 3, 1 dot product 4, negative 3, negative 17. Okay, we're going to show that this equals 0. So 2 times 4 is 8. Plus negative 3 times negative 3 is 9, plus 1 minus 17 times negative 17 is negative 17. Okay, 0 equals 0. Therefore, plane 1 is perpendicular to plane 2. Now, B. Show that the planes, plane 3, which is this, and plane 4, which is this, are parallel but not coincident. Okay? So parallel but not coincident. So that means different d values. Okay? And parallel means n1 is going to be a scalar multiple of n2. That's it. Okay? So let's first identify n1 and n2. So n1 is 2, negative 3, 2. Okay, and 2 is 2, negative 3, 2. Okay, well, that was easy. We can see what's going on already. Okay, and then the d value is negative 1, and the d value here is negative 3. Okay, d value, d value. So what we want to do is we want to see that n1 is a scalar multiple of n2. So what we're going to do is we're going to stack these. We are going to divide the x's, I should call it the a's. The a's, the b's, and the c's. Okay? And we get 1 equals 1 equals 1. Since these are all the same number, okay, they are indeed scalar multiples of each other. It's a scalar multiple of 1, which basically just means the same. We can see that. So these are at least parallel. Now, there's two different situations. There's parallel and coincident where they lie on top of one another, or there's parallel and not coincident or like distinct. Okay, so what we have to do is we have to check the d's. So let's stack them. So we essentially divided these 3. Now we're going to divide these 2. So -1 divided by -3, we get 1/3. Okay, so 1 and 1/3 are not equal. So that means that it's not this exact same plane. So therefore, they are parallel, but not the same, which means coincident. Now the angle between intersecting planes. So the angle theta between two planes, plane 1 and plane 2, with normals n1 and n2 respectively, can be calculated using this formula. Okay, so let's dive right in. Example 5, determine the angle between these two planes here. So what we're going to do first is we're going to first identify n1 and n2. Okay, n1 is 1, -1, -2. And n2 is 2, 1, -1. Okay, and let's just follow the steps in this equation. So first, let's find the dot product. Okay, so let's find n1 dot n2. So we're going to get 1 times 2 is 2, plus -1 times 1 is -1, plus -2 times -1 is 2. So 2 plus -1 is 1, plus 2 is 3. Oh, sorry, I put equals 0. Don't know why. Okay, the dot product is, we'll do this, 3. Okay, now let's find the denominator. So let's find, so that's the dot product. We'll find the magnitude of n1. Okay, so we have 1 squared plus -1 squared plus -2 squared. Okay, so we get 1 plus 1 plus 4, so we get √6. Okay, and then same thing, we're going to find magnitude of n2. So n2 is 2, 1, -1. So we're going to have 2 squared plus 1 squared plus -1 squared, which we get 4 plus 1 plus 1, which is √6. So let's go ahead and put into this equation cos theta equals, okay, we're going to have 3 over √6. So we're going to have cos theta equals 3 over 6, which is 1/2. So theta equals cos inverse of 1/2. So theta equals 60 degrees.